Hi, everybody. My name is Rachel Meidl. I am from the Baker Institute for Public Policy, and I'll be presenting on progressing plastic sustainability through advanced recycling. So I work at the Baker Institute Center for Energy Studies, and we are the #1 ranked university-affiliated think tank globally 4 years running. We are nonpartisan, and we provide data-driven analysis on a range of foreign and domestic policy issues. And our work is designed to help bridge the gap between policy and practice. My work is centered broadly on waste management, circular economy, sustainability, resiliency, and the domestic and global policies associated with it. Weaved into the current narrative of decarbonization, the energy transition, and waste minimization is the idea of sustainability. And it is often misinterpreted, and it is growing in prevalence with society's concerns of the changing climate. And I want to unravel what this actually entails. Sustainability is a feature of a system in its entirety that factors in a wide array of environmental, social, and economic factors, as you can see on the screen. And it assesses how all of these things interact. It evaluates, as examples, geopolitics, human rights, profitable growth, socio-technical capabilities, and many other subdomains. And it involves quantifying and understanding what the risks are, the trade-offs, the unintended consequences of all of these things. And we look at this from a life cycle perspective across the entire value chain. This is what leads to long-term systems balance. And there's very little understanding or application of this in today's policies and decision-making. We oftentimes hear the word sustainable as if it were a property of something, like paper straws, solar panels, even electric vehicles. But things in isolation can actually be sustainable. That's because sustainability entails a comprehensive understanding of the relationship between a complete system and these products, processes, or technologies. And through this holistic outlook, we have a better sense of risk shifting and unintended consequences. We can't optimize individual parts without factoring in the relationship to the system. Focusing solely on the separate parts could open up vulnerabilities by shifting risks elsewhere in the system. Thus, it produces unsustainable and undesirable outcomes. And we need to understand this before we conclude that an action, a policy, a technology, or even a product is sustainable. So what is stimulating all the interest around sustainability? Well, more and more we're seeing industries and governments around the world commit to global climate and sustainability targets and strive for carbon neutrality to meet the Paris Climate Agreement, the UN Sustainable Development Goals, and the UN Global Compact, among others. Corporations and governments are aligning around decarbonization strategies more and more than they were before. And they're building these into their business strategies through corporate social responsibility and ESGs. Our current linear business models, government policies, and consumer behaviors are largely linear, where our systems are designed around taking materials, making products, using them, and then disposing them. Ideally, our goal is to gravitate towards circularity, where we design for durability, reuse, repair, and dismantling. This is a basic concept of a circular economy model, and it is gaining foothold in the political, economic, and scientific fields, and it is being integrated into corporate strategies as well as local and national governments, especially throughout Europe and Asia. The circular economy encourages system innovation that designs out waste, increases resource efficiency, keeps materials in use, decouples growth from the consumption of finite resources. And it does this through responsible sourcing, recycling, reuse, repair, remanufacturing, and other strategies. And the ultimate objective of this is to transition from today's linear arrangement of the take, make, use, and dispose to more of a regenerative circular system where the societal values of products, materials, and resources are maximized over time. I want to highlight new plastic statistics that were published recently that accounts for US plastic exports, illegal dumping, and domestic littering. These figures place US as high as third among countries contributing to coastal plastic pollution. More than half of all plastics that were collected for recycling in the US were exported. And of this, 88% of exports were routed to countries with insufficient solid waste infrastructure. So the amount of plastic waste generated in the United States that is estimated to enter the coastal environment is 5 times larger than what was previously estimated. This is concerning given that plastics generation and the rates and demand is projected to increase 4 to 5% every year. Annually, we generate over 400 million tons of plastic globally, and the demand is set to triple by 2050. The majority of plastics can't be recycled in current systems using our current mechanical technologies. Our plastics are just far too complex. They're multi-material. They're highly customized, they're contaminated, they have additives. All of these things prohibit management in existing systems. So their fate is relegated to incineration, landfill, or export where the management and accountability is largely obscure. And a small percentage that is eligible for recycling within our current systems can only be recycled a limited number of cycles until the material degrades and it's downcycled to lower value products. These downcycled materials eventually have an end of life too, and they meet the same fate of landfill or incineration. Now, although we're extending the use of plastics into other materials through downcycling, and it does align with the principles of circularity, in reality, downcycling to lower quality products simply delays the inevitable, which is landfill or incineration. And this metric of downcycling is not captured in current life cycle assessments or sustainability profiles. So it really skews our idea of what is actually recycled. And this ultimately affects the outcome of what is sustainable and circular. This business model, our current system, is inconsistent with the principles of a circular economy, where we want to keep that molecule in play for as long as possible and maintain materials at an economic value. If advanced recycling technologies are not a part of the way forward, we have to be comfortable with the outcomes of the current linear model, and that's managing waste in landfills, incineration, waste to energy, or a continued abandonment in our ecosystems. So even prior to COVID, there were a number of existing obstacles that were barriers to the waste and recycling industries. The pandemic was just another reminder of how complex and entangled our supply chains are. As mentioned, we had linear business models centered around export, decades of dependence on offshore supply chains, turbulent commodity markets, and waste volumes were increasing every year, and funding for public works and sanitation and waste management were just not keeping pace with generation. We have high levels of contamination and customization that challenge the recycling processes. And then, of course, China's new policy in 2018 that placed restrictions on imports of recyclables and waste exposed our system to a host of other new vulnerabilities that upended our recycling and waste industries. Now, when we think of plastic waste, we immediately gravitate towards consumer single-use plastics. But it's not just typical household items and consumer products where plastics are found. Plastics are integral components to the energy transition, and they can be found in solar panels and wind turbine blades and their components, electric vehicles, lithium-ion batteries, energy storage systems, and electrolyzers to create green energy. These plastics have no or limited end-of-life pathways except landfill incineration or export to secondary markets, where we just shift that waste management burden to foreign economies. Because even though they can be reused, they will eventually have an end of life, and the plastics used in these applications are not recyclable in traditional systems. And so when we look at plastics and a variety of different items other than single-use plastics, 20% of them are in electronics and e-waste that are sent to landfill annually. They account for 50% of the volume of every car, and will become even higher as we try to lightweight vehicles to offset the weight of lithium-ion batteries. They're in 60% of all apparel fibers from polyester. They're in healthcare. Now, while we've developed recovery systems for some plastics, and we've done a great job with certain chemistries, we fail to see the challenge holistically in ways that address the diverse forms of plastics throughout our system and entering the system over the coming decades. This is where advanced recycling could possibly play a role. It has the potential to manage these types of plastics that we haven't yet contemplated or quantified on an end-of-life basis. So there are existing innovative technologies in advanced recycling that have the potential to solve some of these challenges and to meet the growing demand for recycled plastics. Reducing plastic waste by chemically converting post-use and difficult to recycle plastic into their original building blocks that can be continually integrated into supply chains as feedstocks for new plastics and chemicals, other raw materials for manufacturing, and even lower environmental footprint transportation fuels without the need for virgin materials. All of these can play a powerful role in driving a circular economy by creating a closed loop system. It diverts valuable plastics from landfill and incineration. It minimizes fossil fuels feedstock inputs, and it fills the unmet demand for high quality plastics that can be processed in predictable, controlled, and regulated processes with controlled operating parameters. And also polymers can be validated through independent third-party certification. Advanced recycling is rapidly evolving. There are well over 60 technology providers that exist in Canada and US, and nearly all of them are at least at the lab stage of maturity with significant potential to grow and scale. Advanced recycling refers to a broad range of dozens of technology processes, and it has a number of different technology platforms with a variety of different outputs. But in order to gain traction on sustainability, we need to overcome competing priorities that will challenge the idea of system sustainability. Without understanding the important role plastics play in attaining climate sustainability targets, these major initiatives that I listed here will simply shift risks throughout various parts of the global value chain. It'll constrain supply chains and destabilize the plastic market. There's a fundamental disconnect in our society around the economics of hydrocarbons, which are the building blocks of plastics, and the wide assortment of products and energy derived from them for our basic necessities and for the energy transition. Policies like zero emissions vehicles by whatever date that is. Plastics make up 50% of the vehicles I mentioned. There's around 39 different types of basic plastics and polymers that are used to make an automobile. And this is going to increase with the rise of electric vehicles due to the growing demand from the market for high performance and lightweight fuel efficient vehicles. 100% carbon-free electricity, the increased demand for complex multi-material plastics that are used in wind turbine blades and solar panels and electrolyzers and other things are going to continue to increase. And because of the complexity of the plastics that are not recyclable in current systems, these types of plastics will migrate as waste to landfill incineration, or they'll be exported to secondary markets where we lose control of the supply chain. So we have to start thinking about how we can capture these types of plastics in a more circular manner. And then zero waste and recycling goals. Plastics from all of these different advanced energy technologies lack recycling options. So we have an unquantified waste projection that may hinder meeting recycling goals. Current recycling systems need complementary and capable technologies to meet these goals. The existing policies that we have are just not keeping pace with new innovations or the rate of manufacturing consumption. And recycling goals are not keeping pace with the best available technologies like advanced recycling. The waste hierarchy has been the pillar of waste management policy in EPA for well over 30 years. And it is a preferential order of waste management treatment options that prioritizes prevention, reuse, recycling, and recovery over landfill. Waste hierarchy policies and how they are currently interpreted are outdated. Advanced recycling is not seen as a bona fide form of recycling and is therefore ranked towards the bottom tier of the hierarchy along with incineration. The hierarchy, when it was originally conceived and adopted into EPA's waste policies, didn't envision a future scenario that would entail circularity, advanced innovations, or the systems level thinking of sustainability. So governments, should consider amending recycling regulations to incentivize comprehensive use of all materials and all technologies to help manufacturers recognize how to minimize loss and maximize value. For advanced recycling to gain traction, equal treatment of all recycling processes are needed for federal programs. Additionally, there are other recommendations to consider to improve plastic recycling market, and that's improving the economics of collection. Even if advanced recycling technologies are commercially deployed at scale, many of the same challenges inherent to the current recycling system remain, such as collection, sorting, and processing. So we need to finance this portion of the process. We also need to take measures to identify and reduce unnecessary plastics where it makes sense to do so, and using a data and science-driven approach. And the other thing is designing for circularity, standardizing inputs, improving the quality of plastics that enter the recycling stream. And lastly, what I do want to mention is conducting a pilot study and integrating life cycle dimensions into future policies. And I want to drill down on this just a bit more. A feedstock study coupled with a pilot study and properly scoped life cycle assessment can help create the conditions that will determine feasibility, de-risk investments, and address some of these concerns about emissions, waste production, energy resource inputs, pre-processing requirements like moisture control, tolerance for contamination. It'll help us understand how much historical, specialized, or contaminated plastic waste streams exist to maintain the minimum amount of feedstock needed to support an advanced recycling industry. It'll help us understand the generation volumes, the processing capacity in or coming into the state region within a reasonable radius of neighboring states. And then also feedstock quality and composition and the form requirements for each of those advanced recycling technology categories and platforms. We need to understand the system input requirements, the outputs, and as well as the system economics, and the different types and maturity of end markets for these recycled materials. And so all of this will provide a proof of concept and demonstrate the viability of advanced recycling technologies and potential for further scale. Thank you for listening.